All right, so in this video, I plan to go over some questions from our most recent quiz 8. So let's begin. Okay, so quiz 8 mainly focused on Unit 3, Module 1. Which is about the intermolecular forces. Okay, so let's start with question number 1. The question number 1 is, which of the following molecules is most polarizable? Okay, so again, when it comes to polarizability, the polarizability depends on depends on the number of electrons. Okay, electrons and the size. Okay, now the first thing I would do when we get a question like this is to count the number of electrons. When it comes to carbon has 6 electrons and hydrogen has 1, the 4 of them, so CH4 has 10 electrons. And in carbon monoxide we have 6 plus 8, because oxygen has total 8 electrons, therefore it should be 14. And then carbon dioxide, you have 6 plus 2 times 8, which is 16. Therefore, this should be 22. Okay, clearly this is not a valid answer because some of them have more electrons, therefore they should be more polarizable than the others. So CO2 has the most number of electrons. Therefore, we can expect CO2 to be the most polarizable molecule out of the 3 options here. Okay, now let's see, that's our question number 1. Question 2, what types of intermolecular forces are possible between molecules of this type? Okay, again, so to tackle this problem, we need to know what each type of intermolecular forces depend on. So the types of intermolecular forces we know are dispersion forces, okay, which depends on the polarizability. All the molecules, ions, so anything you can think of, we have dispersion forces because they are polarizable. Everything has an electron cloud. Okay, so dispersion is clearly one of the options. All right, if you don't have any option without dispersion forces, that's going to be out. Therefore, option C cannot be a correct answer here because all the molecules have dispersion forces. And then we have dipole forces. Okay, for you to have dipole forces, we need to have polar molecules. Okay, it's because dipole forces depends on the molecular polarity. If you don't have a polar molecule, there are no dipole forces. Okay, and this molecule over here is definitely a polar molecule, because if you think about the electronegativities, chlorine would be more electronegative than carbon. Therefore, chlorine would have a partial negative charge compared to the carbon atoms over here. Okay, so therefore clearly, let's ignore the carbon hydrogen for the moment, because hydrogen is going to be partially positive compared to carbon. Okay, for sure. Therefore, you're going to have, definitely have that going on. But still, because of the great electronegativity difference between carbon and chlorine, 3 and 2.5, I would go with that. Therefore, you should have overall dipole moment going towards the 2 chlorine. So here, therefore, the net dipole moment should look like this. Okay, anyway, that's a net dipole moment. Because that's a net dipole moment, you're going to have dispersion, dipole forces on top of dispersion forces. Okay, so if an answer says dispersion only, that's going to be out at the moment, because we know for sure that we have dipole as well. Now, the last type of intermolecular force is hydrogen bonding forces. Hydrogen bonding forces. Okay, for you to have hydrogen bonding forces, you need to have hydrogen covalently bonded to nitrogen, oxygen, or fluorine, because this depends on the bond polarity of hydrogen nitrogen, hydrogen oxygen, or hydrogen fluorine. Okay, so when it comes to this molecule, you have hydrogens bound to carbons, but not to nitrogen, oxygen, or fluorine. Okay, because you do not have hydrogen covalently bonded to nitrogen, oxygen, or fluorine, you're not going to have hydrogen bonding forces here. Therefore, the last option is out. The only possible intermolecular forces are dispersion forces and dipole forces. Okay, now dispersion dipole. Let's go to this here. Okay, the third question. Third question is about ranking these substances from lowest to highest boiling point. Highest boiling point should have number 3. Okay, let's go here. Okay, now when it comes to all these molecules, they have more or less the same size. And then the electron, even if you count the electrons, I would say that they would have similar number of electrons as well. Now, here's the thing, okay? When we have more types of intermolecular forces, okay, they're going to have stronger overall intermolecular forces in general. Okay, let's make a note. Okay, in general, having more types of intermolecular forces in comparable molecules, with respect to size, okay, leads to stronger overall intermolecular forces. Okay, now when it comes to the middle molecule over here, you only have carbon and hydrogen in this molecule. We know that all intents and purposes, if you have a hydrocarbon or a molecule made of carbon and hydrogen only, it's going to be non-polar. If it's a non-polar molecule, only type of intermolecular forces we can have here are dispersion. Let me call this D. Okay, D stands for dispersion. Okay, then when it comes to the bottom molecule over here, you have a polar bond. The carbon fluorine bond is polar, and also there should be overall dipole moment going towards fluorine, because fluorine has a very high electronegativity, and as a result of that, it should have a partial negative charge compared to the rest of the molecule. Therefore, you should have bond polarity, molecular polarity like that. Okay, so when it comes to this bottom molecule, it's going to have dispersion, because all the molecules have dispersion forces. On top of that, it's going to have dipole forces as well. Okay, so DD stands for dipole forces. And then when you go to the top molecule over here, okay, certainly it's a polar molecule, because you have 2 bond dipoles going towards oxygen like that. Okay, therefore the overall molecule should have a net dipole moment going towards that oxygen. Therefore the overall molecule, I would say, that has a net dipole moment going like that. Okay, so I can get rid of these. Okay, so it's again a polar molecule. All right, apart from being a polar molecule, you have hydrogen covalently bonded to oxygen. So we know when we have hydrogen covalently bonded to either bonded to nitrogen, oxygen, or fluorine, it can participate in hydrogen bonding interactions apart from dispersion and dipole. So this molecule over here at the top, okay, you're gonna have dispersion, dipole, and hydrogen bonding interactions. So HP stands for hydrogen bonding. Okay. Since you have all three types of intermolecular forces in the top molecule, I would say it's going to have the strongest intermolecular forces. So strongest intermolecular forces means you're going to have higher boiling point, higher melting point, higher density, higher viscosity, and then a lower vapor pressure, lower volatility, and so forth. Okay, so the boiling point wise, you're going to have the highest in the top molecule, and then the bottom molecule, you're going to have the lowest boiling point in the middle molecule, because you only have dispersion forces, and then the overall intermolecular forces you can expect to be weaker in the middle molecule compared to the other two. Okay, so with that, I would say this is one, this is the highest, and this is going to be the middle. Okay, now let's move to question 4. Question 4, what is true about these liquids, CH4O and CH2O? Okay, let's take a screenshot and work somewhere else. Yeah, again, CH4O, CH2O. The first thing we should do when we are given a molecule, when we're given the molecular formulas like this, and ask the questions about the intermolecular forces or polarity or anything like that, we need to draw the Lewis structure. It's very important that you start with that. Okay, so if you draw the Lewis structure for CH4, it's gonna look something like this. Okay, and then when it comes to CH2O, okay, it's gonna have this Lewis structure. Okay, now we know the two Lewis structures of CH4O and CH2O. What we need to do is we need to determine the types of intermolecular forces we have, right? Okay, because that is related to the vapor pressure. So stronger the intermolecular forces, the lower the vapor pressure. That's the idea. Now, both of these molecules are polar. Okay, you're going to have a dipole moment in this molecule, and also a dipole moment in this molecule going in this direction. So, okay, both of them are polar, and therefore both of them are going to have dispersion and dipole, dispersion and dipole. But this molecule over here, let me redraw that. Okay, this molecule over here has a hydrogen covalently bonded to oxygen. Okay, which is element from 3 elements, nitrogen, oxygen, and fluorine. Okay, because we have a hydrogen covalently bonded to oxygen, apart from dispersion and dipole, it can participate in hydrogen bonding interactions as well. Therefore, we can expect it to have the strongest intermolecular forces, stronger intermolecular forces out of the two molecules. Okay, if it has strong intermolecular forces, this molecule over here will have higher boiling point, higher melting point, higher density, higher viscosity, and then lower vapor pressure, and then lower volatility. Okay, so now when we look at the answers, the first option says CH4O is likely to have a lower vapor pressure. That is correct. Then CH2O, because IMFs are stronger between its molecule. So certainly the first option seems to be the correct option. Let's read the other ones as well. CH4O is likely to have lower vapor pressure because IMFs are weaker. That is incorrect. Stronger. CH4O is likely to have higher vapor pressure. Nope. It's going to have lower vapor pressure. CH4 is likely to have higher vapor pressure. Nope. It's going to have lower vapor pressure. All right. So the correct answer is the first option. Okay. So the first option. Let's move on to question 5. How many hydrogens in this molecule can participate in hydrogen bonding? Okay, so for the hydrogen to participate in hydrogen bonding interactions, they need to be bonded to either nitrogen, oxygen, or fluorine. Okay, so we have 2 of them here. Okay, just to make sure everybody sees what I'm referring to. Okay, so you have these 2 hydrogens bonded to nitrogen. Therefore, they can participate in hydrogen bonding interactions. Okay, so for an example, it doesn't specify with what molecule. Say that with water molecule. Okay, so we have a water molecule over. Let me see. If you have a water molecule nearby, then what is going to happen is, let me draw the water molecule. The oxygen of that water molecule can interact with this hydrogen to have a hydrogen bonding interaction, hydrogen bonding forces. Okay, so remember, always during hydrogen bonding interactions, hydrogen is going to be sandwiched between nitrogen, oxygen, or fluorine. In this case, this hydrogen is sandwiched between nitrogen and oxygen. Okay, again, we can have another one. Okay, if we have another water molecule on the other side, it can also participate in hydrogen bonding interaction with water. Okay, so, and also just to complete our thought, it's not necessary here. If you want to think about it, so we have another nitrogen. This nitrogen can participate, can actually have another hydrogen bonding interaction with water. Okay, so this water also has hydrogen covalently bonded to oxygen, therefore can have another hydrogen bonding interaction there. Anyway, in this particular molecule, how many hydrogens can participate in hydrogen bonding interactions? Only 2, and those are the 2 hydrogen atoms that are bonded to the nitrogen atom. Okay, so the answer is 2. Okay, let's go to question 6. Okay, you're given a peg diagram. Okay, and then you must determine the where we have strong intermolecular forces in the mixed state or the unmixed state, M state or the UM state, and also what happens when you increase the temperature or decrease the temperature. Okay, will it favor the mixed state or the unmixed state? In this particular peg diagram, both mixed and the unmixed state are at the same potential energies. All right, they are around this value over here. Okay, therefore none of them have stronger or weaker intermolecular. I mean, they have intermolecular forces. They must be comparable to each other. Okay, because if one of them has a lower potential energy, that means it has strong intermolecular forces, and vice versa. But in this case, they are at the same level. Therefore, intermolecular forces must be comparable. Therefore, option 3 is correct here. Okay, and then let me see option 3. And what is going to happen if you other 3 options? If you increase or decrease the temperature, high temperatures favor the mixed state. That is wrong. Because if high temperature to favor the mixed state, then the mixed state should have a higher potential energy. Low temperatures favor the mixed state, and that is wrong. For low temperatures to favor the mixed state should have a lower potential energy. Yeah, increasing or decreasing temperature will not affect this process, and that is correct. Okay, so these are the 2 correct answers, 3 and 6. Okay. Yes, 3 and 6 is this. And let's move on to the last question. How many lone pairs of electrons are present in this molecule? Last question. Okay, so again, the idea is to have a Lewis structure, okay, converting the line structure to Lewis structure, okay. So if that is the case, we need to have an octet of electrons around each of the elements except for hydrogen. So this oxygen, we only have carbon, hydrogen, and oxygen in this molecule. Carbons have the octet, they are implied already, but we need to fulfill the octet around these oxygens. So right now, for an example, this oxygen over here has 2 bonds, that means 4 electrons around it. Then we need to have 2 more lone pairs to fulfill the octet there. Same thing with the other oxygen. There are 2 bonds around that oxygen, that means 4 electrons. We need 4 more electrons, therefore we need to introduce 2 more lone pairs, because they're going to bring 4 electrons, altogether 8 now. Okay, so how many lone pairs are present in this molecule? You're going to have 4. Okay, that should be the answer. All right, so let's do that. Let's submit our quiz. Submit. There you go. We got 100%. All right, I hope this helped. I'll see you guys in class. Bye, everybody.